Hello and welcome to the Unidate podcast on section 18.3 using equilibrium constants. I'm Mr. Sakaguchi
I am Mr. Lin.
and let's start. So um, we can calculate equilibrium concentrations for systems at equilibrium by writing the KEQ expression, and then we can identify our knowns. So when we identify our knowns, we'll have a KEQ and we'll have some of the equilibrium concentrations, but not all of them.
Right. So then, when you identify which ones you do, which concentrations you are aware of, then you can solve for the one missing unknown by just plugging in all the numbers and solving algebraically.
So here we have an example of a problem like this. So let's say we have this system. It's supposed to be at equilibrium, but I forgot to write the double arrow. But let's say, we know KEQ. We have our concentrations of everything except our methane gas. And based upon our equation, we can write our equilibrium expression. And we're given KEQ in the problem. So then we can solve for CH4 by doing a little bit of fancy algebra, which I'm not showing. And then what we do here is we just substitute our knowns for our variables, and we solve and we find the concentration of our gas.
Right. So this is from 18.1. We already showed the basic setup, and remember, it's just product over reactants with the molar concentrations and using the coefficients as turning them into exponents.
Right, so the reason why this is cubed is because there's a 3 in the balanced equation.
Right. Then plug and chug.
There's not only our chemical equation equilibrium, there's also solubility equilibrium. What we have sometimes is we have compounds that completely dissolve in water, we have some that partially dissolve in water, and some that really don't at all.
Right.
And so what ends up happening is with some of these partially or non-soluble compounds is an equilibrium can develop between the particles in solution and the solid that didn't dissolve in the first place.
Right, and the solid that falls out we've discussed about previously. This is called precipitate.
And basically an equilibrium exists between the precipitate and the dissolved particles, and we call this KSP as opposed to KEQ.
Right.
So what KSP is an equilibrium constant for dissolving compounds that don't dissolve well in water. And so, for instance, and you can actually have a KSP for any ionic compound. Just the values will get higher and higher for the soluble ones.
Right.
So for NaCl, the solid, there's an equilibrium that would exist between Na plus and Cl minus if we added enough beyond saturation.
So then what you wind up doing is you just multiply the molar concentrations of the individual ions, and that would be your KSP value.
Now we create our KSP expressions just like we do with our KEQ expressions. So products over reactants. Right. No denominator because this is solid. Remember, solids and liquids that are pure do not show up in equilibrium expressions. So that's why you just see the reactants, the products up here.
Right, because these are, in this case, these are the only ones that are aqueous.
Okay, so let's say we had to solve for the concentration of ions at equilibrium for a saturated solution. So let's say we had silver iodide, and silver iodide, when it dissociates, will dissociate in iodide anions and silver cations. So the KSP expression would be as follows. It'd be the concentration of silver ions times the concentration of iodide ions.
Again, that's because those are our aqueous participants.
And this number 8.5 times 10 to the negative 17th would be something I'd give you in a problem. Right. Okay. Now the one thing to kind of keep in mind here is that if all of the ions are coming from the solid, if one formula unit of this dissociates, for every one of these you have, you're going to have one of these. You're not going to have more of these than these because there's only one source for each of these cations and anions. So these are basically going to be the same number. So this is the reason why I substitute S for Ag plus and also S for I minus.
So as a result of this, since they are in equal concentrations of silver and iodide ions, and we substitute that into our equation for KSP, we wind up with an S squared. And Again, this is all towards our KSP, towards our given value, and you just you solve for S, and in this case, we're just going to find the square root of our KSP value, and we'll find that our silver and our iodide ions both have a concentration of 9.2 times 10 to the negative 9 molarity. Molar.
And yeah, so keep that in mind. Like with these kind of problems, you can end up with, they're going to be relative to each other. We can also predict whether or not a precipitate would form using KSPs. Okay, the way we would do that is we generate our KXP expressions, and then we would put in our given solubilities, our concentrations into the expression. Because we don't know whether or not this is an actual KSP situation, we call it QSP because we don't know.
Right, questionable.
And then what we do is we take the QSP using the KSP equation and comparing it to our actual KSP value. Now, one of three possibilities will arise. If QSP is less than KSP, then the solution is unsaturated and you'll not get any precipitate. If they're equal, then the solution is saturated and again, no precipitate.
And then finally, if your QSP is greater than your KSP, you will form a precipitate.
And what will happen is we reduce the concentration of the ions in solution until it's saturated, or where the concentrations will fit the KSP expression. Okay, so once the precipitate forms, then the system will be in equilibrium again.
Right, which means that your solid precipitate is constantly shifting to the aqueous solution and then back to the solid, but at a dynamic rate.
Okay, so here's an example of where we would actually calculate this. So let's say we have two solutions and we're going to mix them together to see if we're going to get a formation of a precipitate. Now, because we're mixing two solutions with different solutes together, there's going to be a chemical reaction that takes place. And notice this looks like our old double replacement reaction. So our cations and anions are switching partners. We form NaNO3 and PbF2.
Of the products that are formed, PbF2 is not soluble in water.
I'd have to kind of tip my hand and give you the KSP because otherwise you wouldn't know which one to work with.
Right. It'll be given. It'll be given.
So the PbF2 is what we're gonna worry about precipitating. If we look at PbF2 and we have our KSP, we need to create our KSP expression. So for every formula unit of PbF2 that dissociates, you're going to get one lead ion and two fluoride ions. So it's going to be shown by our expression here, where F is squared because of the 2 here.
Right.
Now the molarities are going to be half because we had equal volumes. Remember, once we mix these together, the volume doubles. Right. So the concentration will drop by 1/2. So that's why it goes from to 0.05 and this goes to 0.015.
Right, because now our total solution is
our volume changes.
Yes, our total volume changes from just one solution to two solutions added together. So the concentrations are halved.
And then once we have those new concentrations, we can plug them into our KSP equation. But again, because we don't know the state of the system, we don't call it KSP, we call it QSP. And we substitute and solve, we get this number. And then we compare it to our original KSP number. And because it's greater than KSP, we know that a precipitate will form.
Right. So this brings us to something called the common ion effect. And this is the result, or this is tying in with our previous slide dealing with Le Chatelier's principle in the previous section. And what this means is that when you add in one additional compound that has an ion in common with the rest of the equilibrium, it will cause a shift according to Le Chatelier's principle.
Yeah, so in this example down here, let's say we have an equilibrium that exists between a saturated solution of salt. Okay, if I add hydrochloric acid, it's going to immediately dissociate in water to form hydrogen and chloride ions. If we look at these two systems, the common ion obviously is the chloride, right? And what would happen is addition of hydrochloric acid, because of the common ion, would cause a shift and to the left in this with respect to the salt reaction.
So you can see that because more chlorine is being added, and if we had a teeter-totter here, and we're adding more product, we're going to see a shift towards the left, towards solid sodium chloride. And what you we'll demo this later in class, you'll see that salt will appear and precipitate out of our solution.
And that's the common ion effect.
Yep.